guys, it is Miss Phoebus, and this is lesson 8, and this is about the Moscow Papyrus. We're going to continue on with our ancient Egyptian mathematics, and if you see here in these pictures, I've got a whole bunch of different ancient Egyptian hieroglyphics. The top part here is the actual papyrus, and then this bottom part is the translated piece. Well, actually, it's not translated in English, but it's written out in those ancient Egyptian hieroglyphic number systems and things like that. And then there's also, so the numbers are over here. If you notice, you can see ones, you can see our little tens. Not quite sure, that might be our lotus right here. But we have, this is the numbers, and then with this papyrus, you're also going to see that there are words. There's a lot of, it's almost like word problems, but then they also explain the answer in sentence form, almost like a little bit of an essay. So we're going to look at the Moscow Papyrus, and then we're also going to look at how ancient Egyptians multiplied. So the Moscow Papyrus is an ancient Egyptian mathematical papyrus, also called the I'm going to butcher this guy's name, Golenshichev mathematical papyrus. This guy, Vladimir, he is the first owner of this papyrus that is from outside of Egypt. Look at him in his fancy hat and cane. So he is a Russian Egyptologist who went down to see what he could find and discover, and he discovered this papyrus and called it the Moscow Papyrus. Right now, it lives in the museum, the Pushkin State Museum of Fine Arts in Moscow. He bought it between 1892 and 1893 in Thebes, which is a city in Egypt, and he sold it in 1909 to the Museum of Fine Arts in Moscow. So you could, if you go to Moscow, you could go and see the Moscow Papyrus. I'm glad that they have an alternative name for it, because the G word there, the Golenshichev, is hard to pronounce. So I'm glad that they let us call it the Moscow Papyrus. We believe that it was written during the 12th dynasty in Egypt, which dates back as far as 1850 BC, and the pharaoh Amenemhat III was in power at that time. We do believe it was a much larger papyrus. All that is remaining of it now is only about 18 feet long and between 1.5 and 3 inches wide. We do think that we lost quite a bit of it just due to wear and tear. Does not appear to be burned or damaged intentionally, but it could just have been it's so old and it's made out of papyrus, it's going to fall apart at some point in time. The format, the Moscow Papyrus contains only about 25 practical examples. We don't know who wrote it. The problems follow in no particular order, and their solutions of the problem aren't very detailed. They just kind of talk about how they solve it, not really any formulas, but we do have some geometry in there, and so we're going to explore some of the geometry and how it translates to our geometry today. So one of the things that they do is they created almost like a proportion here called Pefsu, and so you were able to tell the strength of beer or bread in terms of how the grain is. And we've got this hecats of grain that are used to make the bread, and then the number of loaves of bread or the number of jugs of beer that come out of those that amount of grain. That is going to tell you how weak or strong it is. So a higher Pefsu number means a weaker bread or beer. And so there are Pefsu problems all throughout this Moscow Papyrus. So here is an example of one of the Pefsu problems. And so you see these numbers on the side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are the lines to this, just so that you can keep it track and be able to translate between the two. So here is an example of calculating 100 loaves of bread with a pepsu of 20. So if someone says to you, you have 100 loaves of bread of pepsu 20 to be exchanged for beer of pepsu 4, like 1/2, 1/4 malt date beer. So they're giving a ratio of how the beer is created. Then you're going to calculate the grain required for the 100 loaves of bread at the weight, that Pepsi weight of, remember it's strength and weakness. So larger Pepsi weight is weaker. So 20 is not too weak probably, but it is definitely weaker than what you have up here. You're exchanging it for 4, which is a little bit stronger of a beer. And the result is 5 hectat. So we took 100, we divided it by 20, and we got 5. Then reckon what you need for and I don't know what a deci jug is, but maybe it's a decimal jug, like part of a jug of beer, like the beer called for in the 1/2, 1/4 malt date beer. And I know you might be thinking, wow, she's talking a lot about beer, but the water quality in Egypt wasn't that great. But they were able to create a fermented water type source to where the alcohol would disinfect in the water. And so, yeah, they drank a lot of beer back then. So anyway, so they are looking at taking the 4 and turning it into its hectat measure, which is 1/2, and then calculate half of 5, which would be a result of 2.5, and take this 2.5 and multiply it times 4 and get 10. And then, so the answer is 10. You're calculating basically how much you should be able to trade. And so you say, so here's the answer. Behold, the beer quantity is found to be correct. So you don't see, I mean, they're kind of walking you through this and they give you the answer, but it's also kind of vague as to what they're getting at because we don't understand this trading bread for beer and that kind of stuff. We don't understand that portion of it. So it is a little bit weird when we are talking about those kinds of things. All right. So here's another example of a problem, and I love this is considered to be math right here. The example of calculating a basket. You are given a basket with a mouth, so like the mouth of the basket is 4.5. I don't know what the units are, it doesn't tell us. But they want to know the surface area. So this is the work that they use. So they say take 1/9 of 9, since the basket is half an eggshell. Now, I don't know why they're taking 1/9 of 9, but we're going to compare it to what we use in our formulas and symbology. But anyway, they're taking 1/9 of 9 and getting 1, which that makes sense. And then calculate the remainder. So 1 taken away from 9 is a remainder of 8. And then they're calculating 1/9 of 8. So when you do 1/9 of 8, you really get 8/9. But remember that they don't really deal with those types of fractions in ancient Egypt. So 1/9 is the same as 2/3 plus 1/6 plus 1/18. So then we subtract that from our 8 and we get 7.9, and then multiply 7.9 by 4.5, which is the diameter of your basket, and you get 32. Behold, this is the area. You have found it correctly. So there's no formulas here, but what we have down here is we have, I think somebody has tried to figure out how to find the area of this. And so this 256 divided by 81 is actually what the Egyptian mathematicians were approximating pi as. And it was roughly 3.16049, which is relatively close. So you would have that, you would multiply that by, I'm not quite sure, where's the 4? Oh, because it's 4 pi r squared. So 4 would be here, and then we would have our radius. Whereas what they're doing is they're doing some form of this madness, and then squaring it, and then multiplying it by the diameter squared. So we've kind of made this a little bit more sophisticated of a formula, and actually wrote it in formula terms where we have variables and we have things to be able to plug in. So this is our formula for the surface area of a sphere, 4 pi r squared. And we're going to actually use that to figure out the surface area of this sphere. We're actually going to calculate the surface area of half this sphere. So this is the formula that we're going to use, and then at the end we're going to cut it in half. So we have to determine what the radius is, and so in your on your paper you need to have the formula. You need to write what the radius is. So the radius is the distance from, right now they give us the diameter. The diameter is 4. We want the distance from the center to the edge. So half of that diameter, which would be a radius of 2 meters. So we would want to, let me write that not in the purple, but you would also want to write that your radius is 2 meters. All right, then we're going to plug it in, and then we're going to do a little bit of math, and then we are going to, I'm going to let you calculate the final answer. So we're going to have 4 pi, and then our radius is 2, and we're going to square it. Now, you have a couple different options, a couple different ways that you can write this, and you may see both ways on something like the ACT or in a geometry class. One would be where you just leave pi as that symbol, and you do the math around the pi. The other one is where you use 3.14 as the decimal equivalent, kind of, because remember pi has an infinite number of decimal places, so that's really just kind of rounding it and then plugging it in and getting just a solid number answer, but it should be a decimal. Right here for you guys, what I want you to do is I want you to use the 3.14, and you can use a calculator. If you do not have a calculator like on your phone, you do have one on your Chromebook, and if you do not know how to access that on your Chromebook, let me know. But you're going to be taking 4 times 3.14 times 2 squared. You're going to get that, do that order of operations, take care of your exponents first, figure out what this is, do all that multiplication, you're going to get an answer, but then you want half of that, so you're going to divide that by 2. So I'm going to let you figure out what that is. Remember that this is surface area. Area has units squared, so you need to make sure whatever your units are squared. Now, units is not the correct unit to be using, so make sure you know what your units are. But I've got you set up. You just need to finish out that problem. And that would be similar to our basket problem. All right, here's a different problem with the volume of a frustum, and I will actually show you what a frustum is, but well, actually, let me go ahead and show you, and I'll go back. So a frustum is like a pyramid, like with the top cut off of it. And so in the Egyptian picture, they have just this, it almost looks like a trapezoid, or it is a trapezoid, and it's meant to represent this frustum idea. But we're going to go back and read this problem. Problem number 14, volume of a frustum. The scribe directs one to square the numbers 2 and 4 and add to the sum of these squares the products of 2 and 4. Multiply this by 1/3 of 6. So they've got the 1/3 and then the 6 there. They have 2 squared and 4 squared, and then they have added to that the 2 times 4. And so it says, C, it is 56. I think that's supposed to be you. You have found it correctly. What the student has been directed to do to compute is the number. So all of that is kind of the wording. This is the mathematics here. But if you can kind of tell, I think down on the bottom, this side is the 4. And then the top, I think this is the 2. There's some extra pieces here, but I think the top base is the 2. And so we're going to see that it's really involving this short base and this long base. But there is a 1/3, We have to figure out where the 6 is. I think the 6 is the height of this. And so when we actually look at what's going on, yeah, this is the modern picture where this is 2, this is for the height is 6. So that's what's going on there, and that's how they got the volume, how much it holds, that's volume, is 56. So here is their formula. 1/3 the height times base 1 squared plus base 1 plus times base 2 plus base 2 squared. And if b sub 1, that's that top base, is 0, so that means that it goes up to a very point, we get a formula for a whole entire pyramid. So v equals 1/3 height times base squared. So that's if you keep coming up and making it a point at the top, tippy top. All right, so we're going to look at finding the volume of our frustum. So we're going to actually use the Egyptian formula. So you need to write down the formula on a piece of paper for your assignment to turn in. We're going to call, oh, we don't have a height, so we're going to make up a height. We are going to call the this 3, we're going to call it base 1. We're going to call the 7 base 2, and then we're going to make up a height. We're going to make it be 10 feet tall. Doesn't look like it, that's okay. Picture is not to scale. So what we're going to do is we're going to plug in values into our formula. You're going to do a little bit of order of operations. We're going to talk about the units so that you can set all this up on paper and figure out what your answer is. So 1/3, maybe not 10. Let's change it to 9. I like 9 better. Do you know why? Because 1/3 of 9 is a nice number. So we're going to do 1/3 times 9. And then we're going to square base 1. Base 1 is 3, so we're going to have 3 squared plus base 1 times base 2, so 3 times 7. Oops. And then we're going to add 7 squared. Okay, now when you go through and you do this, I would do my exponents first. So I would figure out what's 3 squared, what's 7 squared. You could go ahead and figure out what 3 times 7 is, but you would want to add all these together to get a single number and then multiply all 3 of these numbers together. Now let's talk about units. We're talking about units of volume. So you're going to have your units, whatever they are, cubed. Do not write units because you actually do know your units. So I am looking for you writing down the formula, you're writing down all the important information. I think you even have to write down what base 1 and base 2 are, and then making sure you get your answer with proper units. So that's how you find the volume of a frustum. Topless pyramid. All right, let's do the same thing, but let's do it with the volume of a pyramid. And look, we got height of 9 centimeters, and this is a square pyramid. Now, your pyramids are not required to be squared, but in this case, we are doing one like that. Now, that would mean that this is the height of the pyramid, which we know is 9 centimeters. And this B, this is the side length of the base. Side of base, which is 8 centimeters. And we're going to square that. So volume equals 1/3 times 9 times 8 squared. Again, you're going to go through and you're going to do order of operations. I would take care of my exponent first. Then I go through and multiply everything. And your volume, when you write your answer, has to be in units cubed. So again, you're not dealing with units. Don't physically write out the word units. You have a unit to put in there. All right, now there's a video next to where this video is on how to multiply Egyptian style. I want you to watch it. And then you can come back to this video if you need another example. I think he goes through 2 or 3 examples. I'm going to go through one example, and then you have to do one on your own. And I expect to see a table filled in, I just expect to see the things that you are adding together to get your answer. And I know that you can check it. You could do this in a calculator, but that's not the point. The point is to experience how did ancient Egyptians multiply those values. I wonder if we could watch the video like this. I don't think you can hear it though. But anyway, it's called the doubling method. And so he's going to walk you through um, how to do that. So you will have a table that you have to build. So he's gonna work out some different problems for you. We're gonna work out a problem here, and so we're gonna build a table. Now, what you're gonna do is you're always gonna start with the way that I do it is start with numbers that are multiplied by 2. So I start with 1 and multiply by 2. He starts with, no, he does the same thing. He starts with 1 and multiplies each by 2. So your table should have that. Now, you're only going to use, in this case, the 28. We're only going to use up through 16 because we can't use numbers greater than 28. And so what we're going to do over here with our 51, because we're going to multiply several numbers by 51, is we're going to fill in the table with 51, and then we're going to double it each time. So just like we doubled over here, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. We're going to multiply each one by 2. So 51, and then 102, 204, 408, and 816. And that's where we're going to stop. If we needed larger numbers because we were multiplying 51 times something much bigger, we might need both of these, but we can stop our table right there. So when you do a problem like this, I expect to see the table. The left side of the table should look the same every single time. It's the right side of the table that will change, and it's whatever this right number is. And actually, you're going to do several problems with these, so you are going to be doing writing with several of the numbers that are the same. The number that's the same, that's the one that you want to keep using over and over again in this right column. All right, so what we're going to do is we're going to look at what can we arrange, how can we arrange to get 28 if I look at just the numbers on the left. So I'm just looking over here, and I want to be able to add 1, 2, 4, 8, 16. I want to be able to add to get 28. So if I add 16 and 8, I get 24. 24 is pretty close to 28. I just need 4 more. So 16 plus 4 is 20, 20 plus 8, 28. So we're looking good there. So that helps us set up for what pieces we're going to add together. We're going to add each of these numbers together, and we're going to get the same thing as if we multiplied 28 times 51. So 204 plus 408 plus 816. So 6 and 4 is 10, plus 8 is 18, carry the 1, 2, 10 and 4. So this equals 1,428. So on your assignment, I should see a table, I should see what you are adding together, and I should see your answer very clearly. You can check it with a calculator, that's fine, but I do want to see those components being used. Let's look at another one. We're going to still stick with multiplying by 51, but we're going to change what we're multiplying. We're going to multiply 17. So 17, I go to the left. I can do 17 as, and you can do this a couple different ways, but it should work out every single time. 16 plus 1. So that means I should add 51 and 816 together and get 867. And again, you can check it, but you should have a table. Now, if you keep using the same table, because it's the same numbers, great. But I should see a different addition problem and a different answer. and you can check that answer, but I want to see all of those components. Let's look at, I think I have one more, and it may be a bigger number. It's 56. So with 56, because 56 is bigger, I need to pick up 32. So I doubled 816 and got 1,632. So what I'm going to do is I'm going to figure out what adds to give me 56. So 32 and 16 is 48. 48 and 8 is 56. That's right. So we're going to add all three of these numbers. So 408 plus 816 plus 1,632 is 16, 5, 10, 18, 2,856. And so that is my answer. Again, I want to see the table. So the table should have changed a little bit, or you added onto the table. I should see the addition pieces, and I should see your answer. And that's how the Egyptians multiplied numbers together. And I think it's pretty interesting that it works out that way. All right, I'll see you in the next video. Bye.